A new analysis reveals that the gigantic impact that led to the Moon's formation might have also switched on Earth's magnetic field. Based on the bulk density, Venus and Earth have cores that take up about half of their radius and roughly 15% of the volumes. Researchers don't know if Venus has a solid inner core as Earth does. Don Davis, the New Solar System fourth ed. Planetary scientists don't really know what to make of Venus. Although it's a near twin of Earth in size, mass, and overall rocky composition, the two are worlds apart, so to speak, in many ways. One obvious difference is our sister planet's dense, cloud-choked atmosphere. This enormous blanket of carbon dioxide has triggered a runaway greenhouse effect, trapping solar energy so well that the planet's surface temperature has rocketed to roughly 460 degrees Celsius (860 degrees Fahrenheit). Dig deeper, and the differences become even starker. Based on its density alone, Venus must have an iron-rich core that's at least partly molten, so why does it lack the kind of global magnetic field that Earth has? 2. Generator field. The liquid core need to be in motion, and for a long time theorists suspected that the planet's glacially slow 243-day spin was inhibiting the necessary internal churning. But that's not the cause, researchers say. The generation of a global magnetic field requires core convection, which in turn requires extraction of heat from the core into the overlying mantle, explains Francis Nimmo, University of California, Los Angeles. Venus lacks any of the plate tectonism that's a hallmark of Earth. There's no rising and sinking of plates to carry heat from the deep interior in conveyor belt fashion. So for the past 2 decades, Nimmo and others have concluded that the mantle of Venus must be overly hot, and heat can't escape from the core fast enough to drive convection. Now a new idea has emerged that attacks the problem from a wholly new angle. As Seth Jacobson, now at Northwestern University, and 4 colleagues detail in September's Earth and Planetary Science letters, Earth and Venus might both have ended up without magnetic fields, save for one critical difference: the nearly assembled Earth endured a catastrophic collision with a Mars-size impactor, the one that led to the Moon's creation, and Venus did not. Jacobson and his team simulated the gradual build-up of rocky planets like Venus and Earth from countless smaller planetesimals early in solar system history. As bigger and bigger chunks came together, whatever iron they delivered sank into the completely molten planets to form cores. At first the cores consisted almost completely of iron and nickel. But more core-forming metals arrived by way of impacts, and this dense matter sank through each planet's molten mantle, picking up lighter elements, oxygen, silicon, and sulfur along the way. Over time, these hot molten cores developed several stable layers, maybe as many as 10 of differing compositions. In effect, the team explains, they create an onion-like shell structure within the core, where convective mixing eventually homogenizes the fluids within each shell but prevents homogenization between shells. Heat would still bleed out into the mantle, but only slowly, via conduction from one layer to the next. Such a stratified core would lack the wholesale circulation necessary for a dynamo, so there would be no magnetic field. This might have been the fate of Venus. Thanks to churning convection in its liquid outer core, Earth has a substantial magnetic field. Blue arrow indicates pole direction, yellow arrow points toward the Sun. NASAGSFC Scientific Visualization Studio JPL-NAIF on Earth. Meanwhile, the Moon-forming impact affected our planet literally to its core, creating turbulent mixing that disrupted any compositional layering and creating the same mix of elements throughout. With this kind of homogeneity, the core started convecting as a whole and drove heat readily into the mantle. For that, plate tectonism took over and delivered that heat to the surface. The churning core became the dynamo that created our planet's strong, global magnetic field. What's not yet clear is how stable these compositional layers would really be. The next step, Jacobson says, is to grind through more rigorous numerical modeling of the fluid dynamics involved. The researchers note that Venus certainly endured its share of big impacts as it grew in size and mass. But apparently none of them hit planet hard enough, or late enough, to disrupt the compositional layering that had already settled out in its core. By contrast, the team concludes, Earth was struck violently at the end of its growth, simultaneously creating its moon and homogenizing its core. If they're right, then the divergence of Earth and Venus becomes a classic story of planetary haves and have-nots.